thanks very much for the invitation to speak. It's a real privilege to come here and talk to you about some of the stuff I've been doing with colleagues of mine in the NHS. So a bit of background about me. I used to be in academia, did PhD and then postdoc, and then now work for the NHS in the diagnostics labs there. So if you've ever had a blood sample taken, I work in the labs that actually analyse that. So just a quick poll of the room. Who's actually done any machine learning? Okay, so a good few people. So just to warn you, the first half will probably not be for you, but everyone else. Just a bit of background on the kind of stuff we've been doing, and a bit of background on machine learning. So I think what I really want to put across is that for those of you who haven't done machine learning, is that a lot of the tools to do machine learning are freely available. You can just go and use them. That's not to say they're easy. So going back to Andrew's talk, they're free, but that doesn't mean it's easy to do, right? But it's still accessible. And they're applicable to loads of different kinds of data. So we've been talking about text processing, artworks, images, and also then things like lab data. And I hope what I'll get across to you is that the opportunities in healthcare and medicine are really abundant. And this is really in its infancy at the moment. But with companies like DeepMind and other research labs working on this, I think it's going to be really big in the future. So this is kind of lab-based diagnostics, imaging, and even consultations and history taking from patients. And this is a great quote from a review, which was actually a critique of DeepMind and their handling of the raw free data. But it's a really good review, worth reading. And they just say that machine learning offers great promise in helping to navigate complex information spaces, environments and workflows that are beyond the reach of any one clinician or team. And I think that's the really important thing to take away, is that we're kind of using AI to get at things that are just intractable by one person or one doctor or one biochemist in the lab. So a bit of background on what is machine learning. Apologies to those who already do it, but machine learning uses computers to recognize patterns in data sets effectively at its most fundamental level. There are other applications, and what's really important is that this is done without explicitly programming the computer to do so. So the computer's learning from the data itself. I'm not telling the computer how to pick out the patterns. It does it itself. And there are loads of algorithms available. A lot of them are freely available. Neural networks are really popular at the moment. And they've kind of fed into deep learning, which is a whole new area of research, which companies like Google and Apple and Microsoft are really pushing forward. But each has different strengths and weaknesses. But at its kind of crux, supervised learning, we've talked a bit about unsupervised and supervised, and I'm going to focus on supervised learning. But we're providing the machine an input, some data, a picture of a patient, an X-ray, a lab test result, and we're expecting it to provide an output, some useful information to us. So like a label on a customer feedback, but in terms of medicine, it's, is this a disease or is it normal? So I bet you guys have come across the terms machine learning, data science, and artificial intelligence, and it took me a long time to realize, is there a difference? And if there is a difference between them, what is it? And there's a huge amount of overlap. And I think this guy, David Robertson, summarizes it really well, in that data science produces insights, machine learning produces predictions, and artificial intelligence produces actions. So that's a really nice quote from him. So what can you do with machine learning? We've seen some great examples. The stuff on artwork is amazing, and the customer feedback stuff's really interesting. And I guess this is kind of maybe a poster child for machine learning is the work of DeepMind, which was bought by Google a couple of years ago. And so this is a Korean game called Go, and for a long time it was thought that it's just irreducibly complex and a machine will never be able to play it and will never be able to beat a human. And about 2 years ago it beat a human, and that was the world champion Lee Sedol. And this is amazing stuff. That's the founder of DeepMind on the left there, and the champion on the right. So another really cool thing that was published a couple of years ago was making pictures of cats. If you guys like cats, they also do things like handbags and fascias for buildings. And so you put in an outline of an object, and it creates a picture of a cat, which is pretty cool. Likewise, going back to the artwork stuff that we saw earlier, you can put in an outline of a human, and the machine will take its best guess of what that human actually looked like. So there's a really great talk on Bang Bang Conf on YouTube by this guy, Jeffrey Litt, and this is kind of just shamelessly taken from his talk, but it's well worth watching that. It's really good. And this is the use of GAN, so generative adversarial networks, in upscaling images. So I'm sure people in here have seen CSI, Law and Order, all that kind of thing, when they say, I want to know who this person is, they've committed some crime, or it's a number plate, and they zoom in and they say, oh yeah, I can see the number plate. Obviously that's impossible. Or is it? So this is the real answer, these are the images, and then we can reduce them to low-res versions of those, and then we can give the GAN its best guess. And obviously they don't look, I think the projector's giving it kind of a good look from where you guys are. So, you know, it's pretty impressive. Obviously it's not like a perfect image, but we're getting close. And I think this is really cool. So this was published 2 years ago, and we talked a bit about it, Luba, in the first talk, is converting text to images. So you can give the computer a text, this bird is blue with white and has a very short beak, and lo and behold we get a picture from the computer of a bird with a white beak. Likewise, the bird with wings and is brown and has a yellow belly, and this is what we get, and a white bird with a black crown and yellow beak, and this is what we get. So these are the kind of things that are possible with machine learning. So why are we spending loads of time making images of birds when we could be working on healthcare and medicine, right? I'm joking. You need all this stuff, obviously, as a foundation to that. So how can you do machine learning, for those of you who haven't done it? How many people are programmers and or data scientists in here? Yeah. So you guys, I'm sure, are all aware of all these free data science tools. So there's languages like R and Python, TensorFlow, which is from Google, and Weka. All these tools have great machine learning libraries that you can just plug and play and have a go, basically. So if there's any kind of data you fancy, you can just have a go and see what you can get. So just a quick example for those of you who aren't familiar with it. A lot of machine learning algorithms, people in machine learning won't tell you this, but are decades old. And a lot of the techniques are actually from statistics, and they're also decades old. And a really simple example is linear regression. So if we have 2 vectors of numbers, so we've got x and y, and then we know that there's some sort of relationship between them in the fact that x describes y in some way. We can plot that in 2 dimensions, and then we can generate our linear model from known values of x and known values of y, and we've got a relationship between them. And I think the real crux of machine learning is that given a new value of x, we can predict the value of y, right? So whether that's a continuous variable like a number, or it's a class label like, you know, labeling comments from feedback. So that's kind of regression, so actually coming up with a continuous number, but problems of classification, which are really important in medicine. You know, we're saying, is this a disease or it's not, or is this, do I need to follow up on this or not? And so classification is the problem of assigning a category to a new observation based upon training data concerning instances whose category is known. And Andre covered this in quite a lot of detail. So we've got some example data. We've got 3 features, I, J, and K, and we've got rows, which is just some observations we've made. This could be people, it could be animals, it could be sentences. And then we've got our class labels Y. So given a new observation with 3 values of I, J, and K, can we predict the value of Y, right? So we want to uncover some sort of functional relationship between those 3 variables to predict what Y is. And so we want to end up making this thing in the middle of the classifier to do that for us automatically. So a really intuitive machine learning tool is the decision tree. There's a really, really great YouTube series for those of you interested from the Google developers on YouTube, and this example is taken from that. So if we have our data set, we've got 3 features, mass, texture, and diameter, and we've got our labels, they're apples and oranges. So I want to create a classifier that can predict what fruit it is if I give it a new fruit. Obviously a human can do that really easily, you just go, well, that's an apple. But you can, I mean, a human brain can say, okay, well, apples are in general slightly lighter, they're usually smooth, and they're usually smaller. But a computer can do this using a decision tree. So we can put the data in the top, and then at each node the computer will decide what cutoff best separates those classes, so whether it's mass or bumpy or whether it's bigger. And what's really important though about these decision trees is that they don't really work that well in reality, because reality varies, and this is really important in medicine because everyone's different. Everyone in this room will have slightly different biochemistry, their lungs will look slightly different on an X-ray, and it's really important to model that variability, otherwise we're going to create really crap models that just get the wrong answer. So this is why a guy called Andrew Liao from America came up with this really cool algorithm called random forests, and they work by constructing multiple individual decision trees. What they do is use subsets of the data, so random 2/3 or thereabouts of the data set, and they grow a different tree. So notice the trees are slightly different. because they're picking up on slightly different things in the data set. And each node uses a random mix of the original features to split the classes. So we're really trying to model that variability in the system in the sense that we might end up with a heavy apple or a smooth orange, and we want to try and get the model to recognize that. And so when challenged with new data, each tree can say, okay, well, I think this is an orange. Tree 2 thinks, I think this is an apple, actually. Tree 3 goes, this is an orange, and so on and so forth. And then we can take the consensus vote and say, okay, what's the probability that this thing is an orange, or what's the probability that it's an apple? And we can actually tune that probability threshold, but I won't go into that. And so on consensus, the fruit on the top, the new data, it says, oh, this is an orange. So neural networks, these are, there's a joke that just throw a neural network at its problem and it will solve it, but that's obviously not true. But they're really popular and they're really exceedingly capable models. I mean, most of the top stuff at Google is done with neural networks or the architecture of neural networks. And they're really based on how our brains work. So I don't know how many of you guys study biology at GCSE or A-level. That's 0 hands. So this is what a neuron looks like in your brain or in your periphery. And so you've got the end of the dendrites, and they receive inputs from other neurons. So it could be other axons from different neurons in this big network. And then they'll provide some function. They'll process that signal. They might take the sum of the signals. They might subtract them. And then they use some sort of activation function to say, okay, well, if the signal gets to a certain level, I'll do something. I'll fire, or I'll stop firing, or I'll fire a bit stronger. And so they give an output. So neural networks basically model this by saying, okay, let's say we have two features, the mass and diameter of a fruit, and then they pass them through this hidden layer, which is the neuron, the function within the neuron, and then that produces an output and says, this is an orange, this is an apple. Again, this is a huge field, and you can do loads of reading. I really didn't want to get bogged down in the detail, but I think it's important to mention because these are really, really cool models. So how do we train in test models? We had a bit of it in Andre's talk about F-score and accuracy and things. And what's really important, again, in medicine, because the problem is so important in that we can't, the cost of misdiagnosing someone is so huge compared to, misclassifying a comment on some feedback. We really need to assess how well our models will generalize to new patients, new hospitals, a new, subset of patients within an area of trust. And a simple method to do it we've seen today is just randomly partitioning the data into training and testing. So we just say, okay, we'll train on this data, see how well it performs on this data that it's never seen before. But this requires a huge amount of data to get representative samples of, especially in cases where maybe the disease is only in 1% of the population. You need a massive data set to get enough of that 1% for this to be viable. So again, this word cross-validation is thrown around in machine learning all the time. It's been around in statistics for ages, but it's a really useful technique where we basically do this split loads and loads of different times with different subsets of the data. And so this just in a kind of pictorial format. So let's say we randomly partition the whole data set into 5 folds, so 1, 2, 3, 4, and 5. So for the first round, we train on 2, 3, 4, and 5 and test on 1. Next, we do 1, 3, 4, and 5, test on 2, etc., etc., etc. And in this way, we can say, okay, well, first time it's 88.1% accurate. That's okay. The next time, slightly less accurate, 86.7. Next time is even more accurate because we're just picking out, we're randomly just getting a higher result because of the data it's trained and tested on, and so on and so forth. But then we can take an average and get a real sense of how well that model performs. And you can repeat this loads and loads of times, and you can even nest validations within validations, but I won't get into that. So we talked about this earlier. A lot of medical papers, machine learning, use accuracy, and it's really commonly used to assess performance of algorithms. And this is just, say, I want to predict people who have disease or who are normal or who don't have the disease. So I could say, okay, well, if the machine learning gets the maximum ratio of correctly classified instances versus total number of instances, that's great. But as I mentioned before, in medicine, we often have problems of imbalanced data. So we have, let's say we have a data set of 10 patients, 9 of them don't have the disease, but 1 of them does. So I could go into that clinic and I could say, right, I'm a consultant. And I could say, I don't even need to see any of you. You're all normal. I'm 90% accurate. So give me a medical degree. I mean, which is great. I feel great about myself, but obviously we need to be careful with this. So if you read any papers or read any news stories about this, make sure they're using the right performance metric. There are loads of them out there, but accuracy is often not the right one to use, especially in medicine. So just a few examples. So there was a paper published 2 years ago on stroke detection, and what they did was they took some individuals who were obviously normal, those who'd had strokes, and those who had a disease called Huntington's. So it's kind of like Parkinson's, where basically you have a faulty copy of a gene, and it creates these plaques in your brain, and you start to lose ability to walk and do things normally. And so they got people to wear, I think it was a watch or some sort of wearable tech that had some accelerometers, so picked up on how they were walking, and they collected all that data and then ran it through a machine learning algorithm, and they were able to predict from that data on that wearable device, I'm sure some people have one out there, whether you'd had a stroke, and that's whether the device was on the impaired side or the non-impaired side, because often it affects your left or right side, and predict whether they had Huntington's. So this is really cool. If we could all wear tech and then suddenly it goes, oh, you're having a stroke, you need to get to hospital, you know. Pretty scary, but at least you get to hospital on time, so it's interesting. So this other one, detecting pneumonia. This is a traditionally really difficult problem. So you go into A&E and you say, oh, I've got a chest, I'm coughing up blood, I'm coughing up sputum. And the radiologist does an X-ray, and then they have to say, okay, well, do you have pneumonia or not? And this is, as I said, this is notoriously difficult to do for medics. So what this group did from America, I think it was America, trained a convolutional neural network to actually analyze these images based versus labels of this is pneumonia or this is not. And they can come up with a heat map of where that pneumonia is. And so going back to Andre, this is the F1 score. And you can see radiologists are actually not so great at picking this up. So higher the better, and closer to 0 is bad, closer to 1 is good. So even a trained medic is not that great at doing this. But what's really important to note is that ChecksNet, their tool, was actually better than the average of radiologists. Although there's one really good radiologist here, so I'd want him looking at my X-rays, but anyway. So a bit of the work that I do is on lab diagnostics. So we get urine, blood samples, and we measure various different things. And actually a lot of the data we have is multivariate. So we have loads of different measurements of different chemicals in your blood or your urine. And then we, as a biochemist, interpret that data and go, okay, I think this is suggestive of this disease, do X investigation. So I came into the lab and said, oh, well, why aren't we using machine learning to do this? This would be amazing. And so this is kind of an example of some data we get. This is me or another biochemist, and then they go, oh, okay, well, I think this looks normal. I think this is actually an inborn error of metabolism and needs following up, and this patient needs to come into hospital. Or this is a non-specific abnormality and you don't really need to worry about it, but it's not, bang normal. So we did some machine learning, trained some models, and so giving the models the same data, running it through. I'm a big fan of R. So we did this and trained the algorithms, and then we were able to actually predict disease classification with a mean balance accuracy of 92.6%. Which I thought was pretty good. But this now frees up our time. So instead of looking at all the normals and saying, well, that's normal, that's normal, that's normal, that's normal, we can basically automate that interpretation and spend all of our time on the really difficult cases that require much more of our input. So clinical diagnostics, this is a really cool robot in China. So this guy, I'm not going to try and pronounce it, but he looks pretty friendly, doesn't he? But for the first time, this robot actually passed the, I can't remember what exam it was, but for a medical licensing exam in China. So who knows what's going to be in the future. And this paper that came out 3 days ago, which is awesome, this is from DeepMind again. And so what they did was take images of retinae to the back of your eye. This is what the back of your eye looks like. And ophthalmologists and medics look at this and they can say, oh, there are various bits of data that a human will look at and say, okay, I think, we need to have this investigation or whatever. And so they applied some deep neural networks to this. And I'll just walk through this table a bit. I don't know how well it's come out. Effectively, just from these single images of a human's eye, they could predict your age to within about 3 years. They can predict your gender, almost roughly 100% accurate. They can predict whether you're a smoker pretty accurately. They could actually predict the value of a blood marker of diabetes. So a marker that we measure in the lab for diabetes, they could effectively predict the value of that without going anywhere near your blood, just looking at a scan from your eye. And they can predict things like blood pressure and things like that. So this is amazing. I mean, this is really cool stuff. And this really shows the power of what kind of state-of-the-art machine learning can do in medicine. And so what I want to go back to really is that this quote. And I think the fact that these things are beyond the reach of any one clinician or team. I mean, we may have some medics who can look at an image and go, I think your blood pressure is 160/80, but I really don't think that's true. But I really think these tools will enable us to get way more value out of our data and provide safer, better healthcare. But let's not just say machine learning can do everything, it's amazing, we're going to solve all the problems, we never have to work again. Obviously, computers are still no match for biological systems, and the human brain is the most complex thing in the known universe. I mean, it really is an amazing organ. And we're not even close to modelling the power of anyone's brain in this room. And we generally need a huge amount of data to make robust models. You know, Google is collecting millions and millions of images to make things like ImageNet. And even that retina scan is based off tens of thousands of images. And often this just isn't possible. And yet a human brain can probably do an activity maybe once or twice, and you can do that over and over and over again really easily. So there's obviously something we're missing. And there was a great article, it's a really, really great paper that came out about 3 days ago about why even a moth's brain is smarter than AI. Because they can do something 6 times and they can immediately get it, whereas it takes a neural network millions and millions of images to actually, do that same task. So there's still a lot of work to do. And I want to end on some examples of when machine learning can go wrong. So machine learning algorithms are really cool and they work amazingly. I hope I've convinced you of that. But they're really dependent on the quality of the data you put in. If you put garbage in, you'll get garbage out. So if we go back to that cat algorithm, draw this great loaf of bread. These are, if you just Google pics to pics, hilarious images, and you can sit there for hours. So if you put in an image of a bit of bread with some eyes, we get a cool, fluffy cat loaf thing. It's pretty good though, isn't it? Anyway. Exactly. Likewise, you put in this great outline of a cat. I didn't draw this. I'd like to think I could do a better job, and we get this wonderful looking thing. So again, it's not far off. I mean, a human brain could say, oh, well, that is a cat. I mean, it's not really a cat, but... and then I don't know how many of you have seen Guillermo del Toro's film Pan's Labyrinth. If you haven't, it's an amazing film, worth watching. But if you put in an image of one of the monsters in that film, get this great looking thing. Which again is great, look, it's got the mouth, it's got the eyes, but yeah, it's a pretty funky looking thing. But again, back to Luba's talk, some of this makes artwork and it's some really interesting stuff. So, but what I really want to get across is that, it really depends on the data quality that you're putting into these things. And for medicine, that's obviously really important because the predictions we're making are so important to people's lives. And model bias has real world implications, so not just in medicine, but there was this great article in ProPublica about racism in machine learning algorithms. So whenever you apply for a loan or whenever you work with your bank, or this algorithm was trying to predict future criminals, it's racist, effectively. It's just labeling people who are black, saying, oh, these people are more likely to do a crime. So, these kind of biases that we can introduce to our models based on the input data is so important, and it's really important to be knowledgeable of them to make sure that we don't make these mistakes. A less serious example, there was a Microsoft bot that was based, I think, off tweets, and it was trained on loads of tweets, and they thought, oh, we can make this cool chatbot. Turns out Twitter's just full of racism, so they made this horribly racist Twitter bot, and it had to be shut down. But it was quite funny for a while. And on the subject of data, so the tools I've shown you are free. You can use R, you can use Python, whatever your favorite language is. So where's the value? Obviously there's some really novel machine learning techniques that are coming out of research labs, but where's the value? And the value is in your data. And in healthcare, that's really important, obviously. You go to your GP, you go to hospital, you give a blood sample, you give data, right? And the NHS obviously holds on to that data. and uses it for the right purpose. But it's a very grey area, and I think research into the ethics of machine learning is going to be big, and I think it needs to catch up with the pace at which machine learning is kind of steaming on. And there's this really interesting case of the Royal Free, which is a trust up in North London, and they basically handed over a huge swath of data, patient identifiable data, to DeepMind with effectively no formal agreement of what DeepMind could do with it. And DeepMind said, well, we're not going to do anything evil with it, honest. And I don't not believe them, because they can do some amazing stuff. But I think people need to be really careful about data ownership and who we're handing this data over to and the consent and so forth. So actually, if any of you have had a blood test at Royal Free or any associated GP surgery, your data was given to them and you weren't asked about it. So these are really important things to be aware of. So the future, I don't think it's really about AI, in medicine at least. I think it's about IA, so intelligence augmentation. And there's this great paper in Nature Comms that came out a few months ago about cooperating with machines. And I think it's not about replacing medics, it's not about replacing biochemists, it's not about replacing people in the NHS. It's about combining two things that are synergistic together, a human brain and a machine, to make something that's effectively better and will provide safer healthcare and maybe even more efficient healthcare, cheaper healthcare, etc., for the future with our kind of aging population. And I think, as I've mentioned, the kind of wider implications of machine learning beyond medicine, data access and ownership I've kind of talked to, and coping with increasing automation. And I think as a society we need to be really aware of these issues and we need to start talking about them. So I think events like this are great in terms of getting people together just to see and think about new things about machine learning. And so there's this great academic at LSE who called David Graeber, who writes all sorts of great stuff. But maybe machine learning will be the end of bullshit jobs. And there's a great book that's coming out soon that he's written on this subject. But yeah, so I think it's really important to think about the wider implications of the kind of stuff I've been talking about. And yeah, thanks for listening.
Wow, amazing stuff. So we've worked quite a few times with the NHS in different places, and this seems like quite a long way away from what we saw in acute hospitals in Huddersfield, Great Yarmouth, Wales, quite a number of hospitals in Wales and so on. I'm really curious to know if you've managed to get this operational in an acute hospital at the front door before or in tandem with a senior consultant routing a patient into medical or surgical or bounce back. Is this happening?
So as far as I'm aware, I can't think of a single application where that's happening at the moment.
Okay, let's talk after this, because
I might be wrong, but I think the US is leagues ahead of us on this, as they are with most things, to be honest.
Apart from the insurance, which is
way
further ahead.
So the work that you're doing at the moment, how's that working with the NHS? If you're not working in the acute hospitals, what are you doing with your research?
Hi, so I think, again, similar to Gus, I've worked with the NHS before in like some Meditech kind of applications, but like a natural progression, one might think from, we have these things as issues of like user-owned confidentiality issues. As a natural progression, is there the possibility of users of healthcare services using these data, using these tools and coming to their own conclusions about their own healthcare or about their own health issues and treatments?
Yeah, I can't imagine that the general public would do that. I'm sure that there's a bit of a selection bias in this room, because I think all of us here would be able to do that and probably want to do it. I think it's more of a question actually about education and technological education in kind of coding and technology. I agree. If we were teaching our kids coding in school and we instill these kind of concepts at them at a young age, I think that is definitely possible. But I don't think we can replace a human doctor or medic with these kind of things. I think you need to use both at the same time. So I don't think it'll ever be a case of, I go to the doctor and go, well, something I wrote in Python says that I've got this disease, so you need to give me this drug. I definitely agree that taking ownership of your health data and being able to interpret that, I think in chronic diseases like diabetes, that's really important. Taking blood glucose measurements at home, and that's really helping them manage their own disease. So I think, it's definitely possible, but I don't think it's ever going to replace that interaction with a kind of actual doctor.
On the subject of replacing that interaction and that human doctor within general healthcare, is there a conversation within this field of research about replacing that holistic relationship a user might have with their primary care physician? For instance, if they have a single primary care physician that they might come into contact with, that physician might know about their home life, maybe about their socioeconomic position, and that might inform any decisions they may make about that user's healthcare. Would your algorithms, would your tools make the same decisions if they're not informed by the same holistic relationship with the user that a single physician might have?
Yeah, I think it'll be very difficult to model that and replace that interaction because it's so complex. And I think that, it's not about replacing anyone. It's about, to give that example, a machine might come up with some answer and say, I think it's this. And a human might say, well, I know their socioeconomic background and I know this, so I think this. And I think it's about appreciating that sometimes a machine will be right when a human's wrong, and sometimes a human will be right when a machine is wrong. And I think that it's the combination that's and the synergy between them is where the kind of future lies. I don't think it's about replacing anyone.
Hi, I was wondering if you had any thoughts on the ability to get an AI not merely to kick out an output we want, but to be able to tell us in words we understand what algorithm it was using, or at least an approximation of what algorithm it was using to arrive at that output. So that if, for instance, it turned out that it was going, oh, you're black, that's a 70% chance, that we can go, hang on, not totally happy about that, or can generally have an insight into what it is that it's worked out from the data that's interesting. Yeah,
so there are various tools to do this. So within random forests, you can actually look at, there are ways of looking at what features it's using to discriminate between whatever classes you've got or whatever value you're trying to regress to. And so you basically take out features one at a time and then see how that affects model performance. So if you take out the most important feature and model performance just goes through the floor, you know that feature is really important. So there are ways of doing that. I'm not familiar with things like that for neural networks, but I definitely think there are ways of picking out what features it's using. And that's actually where classical statistics helps us out, because we can run really classical statistical methods to look at what's most different between whatever labels we have.
So this isn't really specifically a kind of medical question, I don't think, but when you were talking about apples and oranges, I was just thinking of how unfair it is what we ask computers to do with this really specific image that we've snapped. And I was thinking, because I'm quite short-sighted, if I see an orange over there and I'm not sure what it is, then maybe I'll move my head a little bit to get some more data, I suppose. And I see that you're kind of like working from X-rays and MRIs and that kind of stuff quite a lot. And then that made me think about, I've got this kind of bad leg, like everyone's got. And I'm really tactical when I go and see the GP about the information that I give them and what order I give it to them in. Like, if I tell them that I'm running, then instantly they're like, oh yeah, you probably got shin splints, Like, so I just wondered if it's important at what point you inject new data into the algorithm, and so that if you've got an X-ray or an MRI and it comes up with like unsure about what's going on here, whether it's important about then you inject some data about that user doing a certain activity or another view of something, I guess whether that data order is important within the algorithm.
So I guess within a specific model, again, maybe this is my ignorance, I don't think there are ways of doing that, but there are definitely ways of kind of stacking models and like hierarchically arranging models so that you can say, based on the prediction of first model, like let's say the first model is just say, okay, screening, what is this, if this is the answer. So you're effectively making a decision tree out of machine learning models. I mean, it starts to get insanely complicated, but yeah, I'm definitely not an expert on that kind of stuff, but I would have thought there are those kind of hierarchical models out there, yeah.
I think you really explained that technical side of that very clearly, because I think I understand the broad gist of it, so thank you for that. I'm actually really technically minded, but the bit that I found most interesting was that you said that you'd managed to get this technique adopted in your lab, and then you also gave the example of a retina thing, and I was just wondering, how difficult was it to get that adopted, and is it officially, are you allowed to officially use it on real data, and also would that retina thing, in your opinion, ever become a sort of diagnostic? I can go into Boots and pay a £5 or 50p or whatever and get them to do that for me, and how difficult would that be?
So I think the best answer to your question is that I haven't got anyone to adopt this, and I haven't convinced anyone. So sorry if I gave you that
But
impression.
you've shown that it's accurate.
Yeah. No. I think in general people are quite resistant to change, and I know I do it sometimes, and it's really hard not to be like that. So I think there's an uphill battle in terms of convincing people, but I think that's the same with any new technology. When lasers were invented, everyone thought that's a waste of time, what can you do with a laser? And now they're all around us, they're in everything. So I think it's just a case of time that will bring people around. But I think the retina thing, I definitely think you could go to your Boots opticians and they could do that. I really think that is...
Would there be sorry, I'm being cheeky, but would there be such a thing as a clinical trial for one of these techniques, like the one that you've proven so far that is at least worth doing a trial on, in your...
I definitely agree, and I think that's where the next step is really to prove the worth of these things, is to do a randomised controlled trial. And to my knowledge, I mean, I don't know the literature that well, but I'm sure there are maybe some cases of it, but there definitely aren't big studies showing that. But I think that's the next step. Because everyone loves a randomised controlled trial. If you say you've got that, everyone goes, oh, okay, I believe you, it's fine.
Okay, we have two questions. I think it was
Yeah, thank you very much for your talk. That was quite interesting, actually, and I'm speaking from my personal experience with the NHS 5 years ago. Almost died, actually, from meningitis. At the time, I was employed by one of the largest telcos on earth. They were implementing what they call the TSR, Telecommunications Strategy Review, which led to OpenReach. And part of my responsibility was to manage offshore development. And in the process, I contracted a virus that was not known in this country. Okay, and I went to my GP. The symptoms were akin to cold, common cold or flu. Went to my GP, he gave me a note, take 3 days off, gave me antibiotics. Over the weekend, I couldn't stand up from bed. My girlfriend called an ambulance, took it to one of the best. The ambulance crew came up. They didn't understand what I was talking about. They saw the notes my GP left. And they said, oh, well, if you want to go to the hospital and enjoy the hospital, we'll take you there. It took the clever observance of a consultant there to take a spinal swaps from me. And then they noticed there was something much more serious. In this country, they never had that kind of thing before. Only elephants in India had that kind of virus. Elephants are domesticated in India, and people ride on them. And sweets and Diwali vegetables are prepared around them. Unfortunately, I was a victim of this. I'd never been to India before. When the cultural tests returned back to the doctors, Professor Moxon is retired now, and he says, have you been playing around with elephants? I said, I didn't understand what he meant. Have you been playing with elephants? you like playing with animals. I said, well, I don't even know the pets. So they said, you play with animals. I said, no. So what you have, you got it from an elephant. And I didn't know somebody was saying. I said, the only elephant I've seen, it was in a zoo. And that was London Zoo. I've never seen a live elephant. And I've never been that close to an elephant. Now, machine learning, you see, this is the area of biomedical informatics that really interested me. What you just, the speech, what you just said now, it's not a definite science, medicine. It's not like physics, it's not like mathematics. You know, even machine learning itself is in its infancy at this moment in time. What they did was there was a data warehouse of pooled resources where samples of these diseases were known. And that's where the King's College Hospital pulled off that from. And that's why I was isolated in the private ward for 6 weeks, you know. And that helps, actually. That's when, to me, see, it narrows down what you just said. It's not perfect at all. All they did was they had access to a data store where there were known issues outside the UK of that, and that's how I was treated. But that was like that in history. Thank you very much. Cheers.
That was really interesting. Thank you. I'm quite interested. I frequently tend to be interested in the bias part of machine learning, and generally the kind of domains that you hear in the media, etc., are very subjective. So things like the legal system, incredibly racist by its nature in America, for example, etc. You get things like we were just talking about the customer feedback. That's generally going to be negative. To me, it sounds like you're working on a very objective rather than subjective data set. What kind of biases do you get in an objective data set?
So in a way, yeah. I mean, I'm of the mind that machine learning comes right at the end. When you get some data, 80% of my time is on visualizing it, getting to grips with it, understanding, doing some unsupervised analysis and really understanding what's happening in there. And I think in medicine or these kind of data sets, which seem objective, sometimes the labels can still be by a clinician. And obviously we try and get around that by saying, okay, we'll get 3 clinicians to do it blindly. And that does help that problem. So there are those kind of biases, like label biases. There are also biases in the assays we use. So one lab might use, I can train an algorithm on a machine that's in one lab and it will give slightly different results to a machine in another lab. So there are those kind of biases to take into account. And also things like, so the data sets I was talking about, gender is a big problem. So the data's like, I don't know, for the sake of argument, 90% female. Then we're definitely biased towards females. And if that's important to the biochemistry, then we need to know that, and that's really important. It's a caveat of the model is that, I don't know, we're not so good for men. So it's those kind of things really, I think, is where the bias comes from. But again, I think understanding your data set and visualizing it and really playing around with it, you really get to understand those kind of things, and machine learning should be right at the end, I think.
If we've got a machine learning algorithm that can more accurately than radiologists predict whether someone's got pneumonia, and it could potentially save lives, do we have a moral obligation to use it as quickly as possible?
It's a great question. Yeah, I think going back to the gentleman's point, we do need. It's on a big data set, but it's on that could just be specific to that data set. And it's the same with, you come up with a new drug and you measure it in one cohort, it has an effect, you measure it in another cohort, it doesn't. So you need to have loads of randomized controlled trials from all over the place and then do a meta-analysis and say, okay, is there an effect of this drug? So I think in those simple cases you can say, okay, well it does perform better than some radiologists. But I think you need much more data to actually be firm with that conclusion. So I think randomized controlled trials of these kind of things, again, the ethics of that is really difficult, because how do you say, okay, you're going to get a medic diagnosing you, you're going to get a machine diagnosing you? Those are the real issues, and that's why we need to start talking about them, because we're definitely going to come up against that at some point in the near future. So yeah.
Are you not just getting both though, and comparing the? Yeah, are you not just getting both and comparing the machine's diagnosis to the physician's diagnosis?
Yeah, I'm sure there are ways of getting around it. And so our example with the lab, so we have like an external quality scheme where we send labs the same sample, and then we see what result they give us and what interpretation they give us. And we can actually train the algorithm or test it on those, so we have like a consensus interpretation.
Because all this data is digital anyway, right? Pretty
Yeah.
much. So how are those trials not just... what is the barrier to those trials just happening with this digital data, I suppose?
Well,
No,
digital in the
I don't really
sense
get
that,
it.
so for using pneumonia as an example, you'd have to have someone presenting to A&E or wherever with pneumonia, and you'd have to say, okay, well, let's use... So it'd have to be prospective. You can't do it retrospectively, like on the data afterwards, because you need to follow that patient's outcome after they've had whatever intervention. So say the intervention is a machine's predicted it versus a human, you then need to follow what happens to that patient. Did they get treated quicker? Did they recover quicker? Did they survive longer, etc., etc., etc.?
Yeah, but at this point, isn't it just about it being correct or not at diagnosis?
Yeah, but I think proving the value of these algorithms is whether that actually has any impact.
But how could that not have an impact?
I mean, it may turn out that...
How could getting diagnosed for pneumonia quicker not have an impact?
well, if it's... Yeah, I mean, it depends on...
Sorry, false positives, is that the issue?
I was just going to say, yeah, so it's about... So the F1 score there is a harmonic mean of precision recall, which is sensitivity and positive predictive value. So if I say, if the test says you're positive, what's the probability that you actually have the disease? And that's just as important as picking up whether you have the disease. So, you know, with that pneumonia example there, the F1 score was what, 0.4 something. So for any number, you know, you're picking up a fair number of the, I can't remember which way around it was, whether it was more sensitive. But let's say it's really sensitive, so it picks up them really well, but it also calls like 50% of the people that have pneumonia that don't, which is just as dangerous.
So my question is, how is this for you, and how is this for you to collect that data, and how big are those data sets? Are those data sets just some kind of 1,000 data records, or are we talking about massive data sets?
So it's a really grey area, and Google got their hands burnt obviously with the DeepMind thing, because you know there are open questions about if you go to your GP and you consent to them taking your blood sample because they've effectively taken your consent when you agree to give the sample, and then that sample gets sent to our lab, and then we run the investigations that the GP asked for, and then we report them back to them, and then in 5 years' time we say, oh, let's see if we can predict whatever from those data. You know, do we need to get your consent to do that? Because you've already consented to have those things measured. It's completely anonymized, so it's a very grey area in terms of collecting this data. Sorry, what was your second question?
How big are the data sets that you are handling?
Sorry.
Maybe that's the question.
They really vary. I mean, the NHS labs here can process millions of samples a year. But for some of the more specialist stuff, obviously the numbers start to dwindle. But for the DeepMind stuff, they're looking at, especially for imaging, it seems to be you can get huge data sets, and you need big data sets for deep learning. So yeah, like tens of thousands.